know that as we grow, the hurdles will be more. Each time we are washed away, we bounce back to the shore. We know we lead the way, keeping odds at bay. See the sunrise tomorrow, inspire the world to follow.
Okay, we are now going to start our lecture number 7. In our last lecture, we have studied the operating principle of shaded pole induction motor and repulsion start induction motor. And today we are going to start our lecture on reluctance start induction single phase induction motor. Now when we have discussed the shaded pole induction motor, there we have seen that the salient pole structure are divided into two sections. One is unshaded part and another one is shaded part with copper band, and with this arrangement in the pole we have produced two different flux. One is main flux and one is short circuited flux which is flowing through the shaded pole, and these two flux has a time difference, and these two flux has a time difference as well as difference in space, and for that we have able to produce very poor rotating magnetic field, and we able to provide the starting torque in case of shaded pole. Now in case of reluctance start motor, my sole aim is to produce just similar to the shaded pole motors to different flux, say phi A and phi B, and somehow we have to create a time difference and space difference between these two flux. Now in case of reluctance start motor, this has been achieved by creating non-uniform air gap, air gap. So by creating non-uniform air gap, we have produced two different flux with time phase difference and space phase difference. Now how this we have made? So let me discuss with the diagram. So suppose this is my rotor. Suppose this is my rotor, and inside there is rotor conductors are there. Okay. So now what we have done, we have made the structure as we have made the structure of the stator salient fold in this fashion. So means in this fashion, this is the salient fold surface, in this fashion. Okay, in this fashion, and here this is the my rotor. Here this is my rotor. So what we have able to done that non-uniform air gap. So there here the air gap is much higher than this part of the pole face. So this part has a higher air gap than this part of the pole face. That means air gap under one half of the pole face is more than the air gap under the other half of the pole face. So this one half is more air gap than this half part of the pole face. And this is my core of the pole. This is my core of the pole, and here windings are connected. So here below the similar construction is there, salient pole structure is there. Okay, here also there is a salient pole with two part, with this part with higher air gap, and another part is with lower air gap in this fashion. Okay, so and there is also core is there, and in this fashion the windings are connected and two terminals and come out, and in these two terminal A and B I have given the single phase AC supply. So single phase AC supply is given to this part. Now if we see in this structure, now there is exist a non-uniform air gap between the pole face and rotor surface. This is the pole face and this is my rotor surface. So the reluctance path varies from stator pole to rotor. So as a result, reluctance is varying. Reluctance is varying because reluctance is dependent on the length of the air gap. And here there is two different air gap length. So the flux path varies from stator pole to rotor. Now what will happen due to this variation of reluctance? Now my question is, what will happen due to this variation? So due to this variation, what will happen? So two flux will produce, one in this part where the air gap length is higher, half of the pole face, and another flux here, another half of the pole face where the air gap length is minimum. Now what will be the nature of that two flux? The flux, suppose this is one flux is phi A and another one is phi B. Okay, so this phi A flux where the air gap length is more, it will be in phase with the current. It will be, if this is my current and this is my phi A, so it will be in phase for the half of the pole face where the air gap length is higher. Another flux is phi V, which is developed for the minimum air gap. So what will happen? No, in that case there will be a larger phase difference between the flux and the supply current where the reluctance is less. So in case of more air gap it is in phase, and for lower air gap a phase difference will exist between the flux and the supply current where the air gap is smaller. Now both this flux, whether it is phi A or phi B, both this flux is producing because of the same current. Suppose I have given the name of the current I to the same current. So the flux across the larger air gap will lead the flux across the smaller air gap. So for same current, so if this is my phi A, so this will be my phi B. So what? Phi B is lagging, say suppose alpha or beta angle, leading with respect to the phi B. Now for details explanation of this motor, what we will do, we will implement the transformer equivalent circuit concept. So suppose I have taken here two core. Okay, here we have taken two core, suppose. So here we have taken two core. One is air core and AC supply V has provided, the current through it is I, and the flux is phi A. Okay, so suppose we have taken a air core. Okay, so what will happen? As because this is a air core, so there is no I square R loss is exist. We can assume that. So there is no I square R loss. So when there is no core loss, it is air gap, no iron is there. That means the circuit or the coil can be assumed to be purely inductive. So this is a purely inductive coil, purely inductive coil. So in the equivalent circuit, we don't have to represent this core loss because it is a purely inductive coil. So we don't have to represent through any resistance in the equivalent circuit. So if we draw the equivalent circuit, so it will be like this. Okay, so for this inductive circuit, we know what is the phasor relation. 90-degree phasor relation exists. This is my current, this is my voltage. Voltage lead the current by 90-degree, or current lag the voltage by 90-degree, and through this axis the flux is acting. Okay, because the entire current I creates the magnetic flux phi A, so both are in phase. The entire current is producing this flux, so both are in phase, same phase. Now consider a iron core. Let me see what will happen. So now suppose I have taken a iron core. Okay, so this is my iron core, this is my iron core, and I have given the supply here V. So current is I. and the flux is producing is phi b. Now I have taken one iron core. Now this iron core, for this iron core we cannot neglect this I square R loss. We cannot assume this as a purely inductive circuit. That means some equivalent resistance is also exist in the equivalent circuit to represent this core loss. So some equivalent resistance is exist for this iron core to represent the core loss. So if we draw the equivalent circuit, it will be like this. So this is my AC voltage source. So apart from reactance, inductive reactance, there also exists a resistance to represent the core loss, similar to transformer parallel shunt branch equivalence in the equivalent circuit. So this is my R, this is my X, this is my IM, and this is my IC. Okay, so thus the main current I has two components, because here apart from this inductive reactance, also the resistance is present to represent the core loss, because you see it is iron core, it is no more the air core thing. So the flux 5 is producing because of this magnetizing component of the current. So this magnetizing component of the current is responsible for the production of the flux, and this IC current is representing the core loss. So this phi b will be in phase with IM. So if I draw, so this is my V, this is my IM, and phi b is in phase with this IM. And core loss, this resistance is IC is representing the core loss component, so it will be active component, so it will be remain in phase with the voltage. So now this is my resultant current I, and the angle between the current and the voltage is alpha. So here we can see that the flux is lagging the current by some angle alpha. So when here it is air core, it is in phase. When it is iron core, it is lagging the current by some angle alpha. Now with this background, in this reluctance start induction motor, there are two portions. One is having lesser air gap, one half of the pole phase lesser air gap I have mentioned, and one part of the pole phase has higher air gap. So which has lesser air gap, that part has more amount of iron. So where the air gap is lower, that will behave just as a iron core, and where the air gap length is much higher, that part will behave like a air core. So now I have seen, rather we have seen that two flux for the same current, this is my current I, this is my current, this is my current I, okay, this is my phi IA, and this is my phi B, and angle between this is beta. So the flux which is producing due to the more air gap lead the flux which is producing due to the lesser air gap, right? So this is we have seen. and again we are seeing that the axis are of these two fluxes are not same. So we have conclude from here, so between these two flux phi A and phi B there is a space difference, space angle, and there is also a time difference, and these two is essential for the production of rotating magnetic field, because phi A will lead phi B by angle beta. So phi A will reach its peak first, it will reach its peak first, and after that phi B will reach. So this is my phi A, this is my phi B after beta angle. So this angle is basically beta. So after beta angle phi B will reach its peak. Thus in the air gap there are two flux are at certain time phase difference, a space phase difference. So interaction of these two flux will develop a rotating magnetic field, as we have seen in the concept of production of rotating magnetic field. And the rotating magnetic field is rotating from longer air gap region to smaller air gap region, because this is for longer air gap region, this is for smaller. So it will rotate from longer air gap region to smaller air gap region. So this will enable the rotor to start in the same direction as the rotating magnetic field. Now once the motor is continue to rotate, it will act just as a single phase induction motor. Now as the pole structure is fixed, I cannot change the pole structure. So in this reluctant start motor we cannot change the direction of rotation, we cannot change it the direction of rotation. So where the very low starting torque requirement is there we use the reluctance type motor, okay, where the starting torque is very less. So this is the working principle of reluctant start induction motor. Okay, so let me go to the slideshow of my PPT. So this is this is all I have mentioned. Okay, I have mentioned in the discussion. So this is all about my reluctance start induction motor. Okay, thank you.